And I would like to request Professor Rahul Mitra to introduce Professor Purushottam Chakraborty formally.
So it's a pleasure for me to introduce Professor Purushottam Chakraborty, who is a former senior professor of Saha or nuclear physics. If someone has interacted with him earlier, people they may know him already. So he was also a former adjunct professor of physics at the University of Pretoria in South Africa. And he is considered one of the world's leading experts in ion beam modification and ion beam analysis of materials. And he was awarded the most eminent mass spectrometrist in India by the Atomic Energy Commission of India. So you can see the extent of his expertise, and his research includes atomic collisions in solids. Yeah, I'm sorry for the interruption because the mobile I actually touched something. So his research includes atomic collisions in solids, secondary ion mass spectrometry, secondary neutral mass spectrometry, molecular ion SIMS, X-ray and ultraviolet photoelectron spectroscopy, OJ electron spectroscopy, Rutherford backscattering spectrometry, and X-UV optics, nonlinear optics, photonics, and molecular beam epitaxy, and low dimensional materials and nanostructures. So you can see the extent of his expertise. He is guest editor of 2D Materials Perspective, and also he is an editorial board member of International Journal of Modern Physics. Additionally, he is a visiting professor at the Department of Physics, Sultan Quebec University, and honorary professor of physics in University of Pretoria, visiting professor at Catholic University at Rio de Janeiro, guest professor, and he is basically associated with many universities around the world. In addition, he is also fellow of West Bengal Academy of Science and Technology, fellow of Indian Chemical Society. He was awarded Acharya Prafulla Chandra Roy Memorial Award by the Indian Photobiology Society. He is visiting professor of IIT Tirupati and UGC visiting professor of Tezpur University, and also he is many other places. He is so, and recently has edited also a few books. So with this brief introduction, I will stop here because there is a biodata is very big, and there is a lot to. At least 4 or 5 books are there which he has either edited or written. So with this, I invite Professor Purushottam Chakraborty to come and deliver his lecture, for which we are eagerly waiting. Thank you.
এটা দিয়ে যাওয়া ব্যাক করা এটা তো ঠিক আছে এখানে কি পাঠানো ঠিক আছে Can I start? Good morning everyone. My pleasure to come here in spite of very personal difficulty which is beyond expression. My wife is seriously ill and I decided not to come. and my mental state is not even well. But I came because Professor Mitro requested me. I couldn't decline finally. I worked on the SIMS, secondary ion mass spectrometry, since I started my PhD work. I built a SIMS equipment myself at Saha Institute of Nuclear Physics, and that was a part of my PhD program. And for that, Calcutta University awarded me Premchand Roy Chand Scholarship. And that was the first time in India I built a radio frequency quadrupole mass spectrometer, which was used as a part of the whole SIMS equipment. That time, nobody knew about the ultra-high vacuum, 10 to the minus 9, 10 to the minus 10 millibar pressure. I first built the whole equipment, which was really ultra-high vacuum equipped machine. But I cannot show you that machine, but that machine has not been anymore, is not existing anymore. But I will show you another equipment which has been commissioned in Saha Institute, which is a radio frequency quadrupole mass spectrometer based SIMS, which is also configured by myself and built by UK, a company. I will show it gradually. This is a general talk I decided to show you because this is not specifically on the time of flight SIMS, but it is a SIMS. Because time of flight is a technique, okay, for the mass analysis. But SIMS is the whole technique, the secondary ion mass spectrometry, which is basically used for the quantification of materials. And it is the most powerful equipment known to us even now, which can quantify even the parts per billion concentration of material in a material, okay? So for that, SIMS is the most powerful. And we have done, of course, we have analyzed many sorts of materials, including quantum structures, nanostructures and quantum structures. And I will show you gradually what are the steps. This is my institute, a part of my institute. What we are doing basically, we have done, mostly we have fabricated quantum structures by self-assembled way, self-assembled nanostructure. As you can see, pointer ache, lighter ba kichu na thakle kono অসুবিধা নেই মাথা ঠিক আছে okay. As you can see here, that's the above is schematic representations of the self-assembled nanostructure, which is basically a silicon 111 7x7 reconstructed surface, and this is a stepped silicon. If you, for example, this one, you can see this staircase structure. If you start with a staircase structure, and if you allow the atoms to grow on that, atoms will try to follow. It will be automatically, it will be self-assembled, and it will flock around across the junctions of the staircases. So you can grow the quantum wares, and initially you can have the quantum dots like this kind of calcium fluoride quantum dots, and these are very systematic quantum dots that we can grow by the MBE method. But I will show you. Okay, this is not necessary at the moment, but you know, for the quantum structure, the electron is confined in a quantum mechanically confined. So the classical physics doesn't hold good in this case. And you can see energetically, the energies are quantized. And so energy for nth quantum number is n square h square by 8 ml square. So for n is the quantum number. As you can see, for n equal to 1, it becomes h cross square pi square by 2 ml square, which is the minimum energy in a quantum system, which is not zero. So this is contradicting to the classical system. In a classical system, you can make a particle motionless. So you can make the energy zero. But in the quantum mechanics, you can never do that, isn't it? So this is the thing. This is what we actually grow. We are making single quantum wells or the multiple quantum wells. These are the interfaces. This is gallium arsenide, which is sandwiched by aluminium gallium arsenide. This is a quantum well, and we can even grow the multiple quantum wells. We can repeat this kind of structure. As you can see, this has a lower band gap, gallium arsenide, compared to the band gap of aluminium gallium arsenide. Naturally, this is the energy diagram. You can see this is the band gap of gallium arsenide, and this is the band gap of aluminium gallium arsenide. So naturally, this is a quantum well. So you are forming quantum well. This is the conduction band, quantum well in the conduction band, where electrons are confined, and this is the quantum well where the holes, positive holes, are confined. Now the point is this is a very good for the devices, electronic devices. And if you repeat this kind of structure, you can prepare multiple quantum wells which can be used for quantum lasing applications. But mostly what happens, aluminium is interdiffused through the interface. Aluminium gallium arsenide is interdiffusing into the gallium arsenide, and the interdiffuse gets broadened. So SIMS is coming into that picture. Without SIMS, it is impossible to know how the interface look like, how the interface gets fuzzy, how the interface is broadened, what is the broadening, and where the aluminium has been concentrated, what is the lateral concentration or the in-depth concentration of aluminium, that you can measure. So it is very important. The SIMS is coming because SIMS can detect the concentration of any element or any impurity, even oxygen or any kind of element in the periodic table, or even compound across the depth. You can pinpoint the structure, you can pinpoint the concentration distribution within a material. I should skip because there are so many here. We can prepare multiple quantum wells, like this, multiple quantum wells, and this has been used for the quantum lasing applications. Okay, this is the MBE machine schematic diagram, and this is the machine what we have installed in our laboratory. This is a very modern molecular beam epitaxy machine where we are growing atomic structures. We are really making 1 angstrom to 2 angstrom thickness of the film. We are growing. We are able to grow now to 1 to 2 angstrom thickness of the film. For it, like a single monolayer of atoms, we can grow by this technique, MBE technique. And now you can see, this is a structure what really we have been able to grow. This is the gallium arsenide, this is the aluminium arsenide, this is the gallium arsenide. You can see, can you distinguish? Because all atoms are periodic and they are matching. All the atoms of aluminium arsenide have completely matched with the atoms of gallium arsenide. So this is called epitaxial growth, where you can epitaxially grow. You can mimic the structure. You can mimic the crystalline structure of your starting substrate. And you can, your grown film, for example, you start from the gallium arsenide. You are growing aluminium arsenide. This aluminium arsenide is mimicking the crystalline structure, crystalline orientation of gallium arsenide. This is the epitaxial method. And this is the cross-sectional TEM machine of our institute, where we are really doing the cross-sectional TEM of germanium silicon quantum well structures. This is not the topic I'm going to have come here to discuss here, but this is simply just a recapitulation. As Professor Robibroto Mukherjee already told, there are many techniques. For example, XPS, Rutherford backscattering, secondary neutral mass spectrometry, like the atomic probe microscopy, there are any techniques, Auger electron spectroscopy, but SIMS comes somewhere here. And somewhere here where you have, you can see from the chart that these are the techniques where the incident particles in the SIMS can be argon, gallium, cesium, oxygen, gold in the SIMS. So I start from what is SIMS? I start from the very basic idea of SIMS and what is the difficulty in SIMS. In spite of the most powerful technique, we know the SIMS is the most powerful technique, but we have to suffer a big problem in the SIMS. While doing the SIMS experiments, everyone suffers from the matrix effect. And for that, it is difficult to quantify. Nobody can quantify unless you can compensate the matrix effect. Okay, because we have to know precisely the quantification. But quantification is impossible unless you solve the matrix effect problem in SIMS. And that's why SIMS is the most difficult problem now across the whole scientific institutes, scientific community. Because how to solve this problem? And this is the technique what we have developed. And this technique has been able to solve the matrix effect. I will come back. I will come gradually. And then this kind of molecular SIMS, where N could be 1, 2, 3, 4, etc., these kind of molecules, if we detect these kind of molecules in the secondary ions, these molecules are really, they are not being affected by the matrix effect. I will show also. And how to make the interface analysis of materials and quantum structures using this kind of molecular SIMS. Okay. I think time is not that much, so I should not go on. This is an animation that primary ion is being incident and the secondary ions are coming off, you know. So because this is a sputtering process, and so the particles get cut, you see. So the primary ion, it's bismuth trimer. Okay? It's a bismuth, 3 bismuth atoms bound together with a single charge. So this bismuth is incident and it is going down. This is the top monolayer and this is the second monolayer, etc. And it is going down and it goes in a zigzag way by making collisions and collisions. So the first collision and then second collision, it can be knocked out and it's again going down this way. It will make series of collisions. So you know it. So there are many, hundreds of collisions are happening within. It's called the collision cascade. So this collision cascade is a part of SIMS. One has to understand what is collision cascade. And a part of the collision cascade is coming from the lows, from the bottom, and eject some of the atoms sitting on the top surface, they can be ejected. Because the momentum, the part of the collision cascade, if they can transfer the momentum or energy, which is more than the surface binding energy, that those surface atoms, top atoms can be ejected. Now, these atoms are neutral, okay? So, almost 99.999% atoms are neutral, what are emitted in the SIMS process. So, only 0.0001% are ionized. So, it is very difficult because the ion emission cross-section is important in the SIMS. That's the most important part, actually. Because as I told you, 99.999% are the neutral atoms or neutral molecules what are emitted by the SIMS, by the sputtering process. Only 0.0001% are the positive or negative ions. You can see, you can even have this kind of dimer, or you can have this kind of trimer. They can also be ejected in the SIMS process. So if you look at the spectrum of SIMS, you can see there are single atoms, or the dimer, trimer, or it's even clusters. So you can see peculiar kind of species in the same spectrum. Okay? As you can see, the primary ion, the primary ion is ultimately buried somewhere at the bottom. Somewhere. This is called the implanted ion. The ion got implanted. But eventually, the secondary ions are coming off, including electrons. And this is called the collisions. This is one jurisdiction of the collision cascade. So many atoms are all in motion. So these are the single collision cascade. This is the collision cascade, single collision cascade, overall volume of the collision cascade. So all the collision cascades can be independently disconnected, or the collision cascades can be connected. But the secondary ions can be, they are coming from the topmost atoms. You have to know this, that secondary ions what we measure, they are actually coming from the topmost atoms. They are not coming from the atoms below. Because the collision cascade is transferring momentum, transferring energy to the topmost atoms. And if the surface binding energy, if they cross the surface binding energy, they can be ejected. So it's a purely sputtering process. As you can see, this is the primary beam, and you can have lots of positive and negative ions, including electrons, including photons, so many things. Neutral atoms, positive, and eventually the one monolayer has been removed. Actually, we're digging the soil, for example. Okay? So the monolayer has been removed. Second monolayer has been removed. And third monolayer has been removed. Finally, you have been able to make a crater. Just make a crater. So you have to know the crater depth by, you have the stylus measuring stylus to know the crater depth. You can convert the time into depth, so you can finally get the concentration of the element what you are interested to measure. Because it can be, there are many elements here which are buried within the material. They could be impurities, those could be any kind of elements what you want to know actually. So you can really pinpoint the element what were buried there in the materials. For example, indium has been doped in silicon. How do you know the indium concentration in silicon? You have to do the SIMS experiment. You have to measure the indium intensity, which is basically converted into the concentration, and you are measuring as a function of time. And finally, the time can be converted into depth. So you actually are measuring the concentration as a function of depth. And you can do even the 2D and the 3D imaging. 3D. You can do imaging also. Secondary ions can be imaged, and you can get the imaging. You can make the 2D imaging, and if you go on scanning, if you go on as a function of time, your time is passing on, and you are gradually going down and down. So you are getting the 3D imaging also possible. Okay?
Sir, can I ask a question?
Yes.
Sir, what you are basically telling, I guess this is the depth profiling.
If you want to do depth profiling, then after, but it always happens.
Okay. So my second question is, yes, our instrument also has a profilometer, but it's a separate profile.
Yes.
So I have two questions basically. So number one is, you have to basically take the sample out of the SIMS chamber.
After the experiment is done.
After the experiment is done, then you place it in the profilometer, and then do the depth measurement.
Yes.
So one very practical problem, I am a hands-on experimentalist, that's why I am asking this. How do we locate that position? If you throw light on that, is there any technique, or it's just on the expertise of the operator?
Stylus profilometer. That is a computer control setup. You can see in the screen.
So somewhere you have to see.
Yes, you can see in the image.
Another question I have, I think you are the best person to ask. So why generally every SIMS machine is supplied with a profilometer and not an atomic force microscope? Because for the type of depths you create, 1 layer, 2 layer, 5 layer, an atomic force microscope is far more precise than a profilometer. So your thought on that? Is it cost or is it like SIMS was invented before AFM existed? What is the psychology?
AFM is of course possible.
AFM came up in 1986. SIMS is an older thing.
Microscopy, of course you can measure, but once you have already you have already done this kind of crater. The
No, I
crater
understand. So
has already been formed.
no, crater is created in the SIMS.
Yes.
You measure the depth in the profilometer or on the AFM.
Yes.
So generally wherever I see a SIMS, and I have seen that in Cambridge also, it is invariably right next to it is a profilometer. Profilometer is faster, and probably when SIMS came up, AFM was not there.
No, that is because after your experiment is over,
Then your sample is
then you have to immediately convert the time
yes.
into depth. But for that, this is the most handy and most quick method.
AFM will take time.
Yeah, AFM, but that's another experiment. You have to set up the experiment and you have already created, AFM, atomic force microscopy, of course you can get the idea of the depth. Of course you can do that, but that will be much more time consuming. It is much faster and more quicker way of measuring the depth of the crater.
Sorry for this strange question, but I
No, it's okay.
ask somebody.
No, it's okay. It's okay. So this is actually these are the 3 monolayers. This is called the sampling depth. This is called the sampling depth. We are detecting the secondary ions, okay, which have long energy distribution. The secondary ions which are what are coming off from the surface, they have a long energy distribution, starting from the 1 eV or maybe 0.0 eV, 1 eV to 10. Oh, yes. So essentially, you can see the secondary ions are coming from these 1 or 2 or 3 monolayers. So that's why it is called the sampling depth. Okay, but the ion which you are using as an incident ion, that can be buried here or here or here. So this is called the penetration depth. This is a structure. These are the atoms. First layer of atoms. This is the second layer of atoms. Third layer of atoms. Fourth layer of atoms, so on. And you can see this is the primary ions. You can use argon. I do not know what primary ion you can use in your different machines, but normally argon, oxygen, cesium, gallium, all these are primary ions what can be used for the ion bombardment. Then you can have all emissions are happening, and you can then have the mass spectrometer, which could be either magnetic or radio frequency quadrupole or a time of flight. Okay, this could be even time of. This is a magnet. This is a sector magnetic field, as you can see, because this angle is a sector angle. So this is secondary ion is entering, and secondary ion is mass analyzed and coming off from here, and then it is passing to the detector. Okay, but this could be either sector magnetic mass analyzer, or it could be radio frequency quadrupole mass analyzer, or it could be a time of flight. Okay, so but this is only a part of the equipment. This is the time of flight, but the whole thing is common. Okay, the primary beam ion gun or the ion source, if it is a time of flight, it could be pulsed. But for the other SIMS, it may not be pulsed. It could be continuous beam. But for the time of flight, it should be pulsed. For every pulse, you get the whole spectrum. Very quick. Okay? And second pulse comes, you get again the whole spectrum. be argon, could be oxygen, could be.
Yes, but why oxygen? Because oxygen can be a
I'll be telling those points. Sure. This is an important question. Oxygen has to be used. For any instrument, oxygen has to be used. Otherwise, you will have a big problem if you don't use oxygen. Because there are elements which are not responding without oxygen. You have to use oxygen. Okay? Because electronegative element, for example, electronegative elements are responding very high, quickly, very high with the many elements are responding to the oxygen, because oxygen is electronegative. Because you get the spectrum, no? You get the spectrum. So there is intensity of the secondary ions. So the intensity, some of the elements have the very lowest intensity, and some of the elements have high intensity. But what we want to do, we want to get the high intensity. So the intensity has to be magnified, or intensity has to be amplified using oxygen. Because oxygen, the effect of oxygen amplifies the intensity. I will.
I have a question. To amplify the intensity, is there any possibility to do a substrate biasing?
No. I haven't told that. I told, if you have a top surface of any film, okay, there are some elements which do not have an appreciable intensity with what you can measure by the SIMS. Okay? For example, copper. You are measuring the copper plus by the SIMS technique. The copper plus, you see the copper plus signal is so small that copper plus is not detectable. In that case, if you use the oxygen instead of argon or cesium or gallium, if you use oxygen, the copper plus intensity increases almost 3 times or 4 times or even 5 times or even 10 times. This is called the effect of oxygen. Okay? So it depends on the electropositive or electronegative. If the copper is electropositive, because oxygen is electronegative and cesium is electropositive. I'll be back on those topics.
So instrument has the provision to change the primary ion source, or it will be only one ion source on the instrument?
No, it's possible. It's possible. Okay, okay. Only thing it's important for you to know actually that this is the most important expression in the whole SIMS. This is a very simple expression. This is a simple expression. What are the total number of particles sputtered due to the ion bombardment? This is called the sputtering yield. How many atoms have been sputtered due to a single primary ion? Okay, do you understand my point? This is called the sputtering yield. How many atoms have been sputtered? How many atoms have been sputtered due to a single primary ion? Okay, so this is expression. U is the surface binding energy. U is the surface binding energy, and this is the very important parameter. This SNE is called actually nuclear stopping power, because the SIMS is a nuclear collision region. Energy of the primary ion is such that it is not really making any kind of electronic cross-section. Electronic interaction is not happening in this. Nuclear stopping cross-section is applicable, where the stopping cross-section means for the energy loss per unit length. So this is the stopping cross-section, is the rate of change of energy of the primary ion as a function of depth. So this is negative because as you go deeper, energy is getting less and less, so it is minus. Okay, I'm not telling you. So these are 2 modes of SIMS. We have to now tell you this. There are 2 modes of SIMS, static and dynamic. So in the static SIMS, you have the primary current in the order of picoampere per centimeter square, and where the very low erosion rate. Erosion rate is extremely low. And you can do the surface analysis. Like the time of flight SIMS, for example, it's a static or dynamic, you know it? The time of flight SIMS? It is static, why? You know it? Why it is static? Because very low erosion rate. Also the primary current is very small, very low. So erosion rate is very. Now, you can see, is essentially only the top layer is confined. During your whole experiment, for 3 hours or 4 hours or 5 hours, you can confine across the top layer only. You are not destroying the material, no damage practically. So it is the static SIMS.
Sir, same instrument can work in both static and dynamic mode.
Yes. Because you are tuning only with the primary ion current and primary ion energy. So depending on the primary ion current or primary ion current density, you can make it static or you can make it dynamic. So if your current density is higher, you can make it dynamic. Dynamic means you are eroding the layers. You are removing the top layer, second layer, third layer, it's getting dynamic. Okay? And high erosion rate. And you can do, but if it is dynamic, you can do the depth profiling because you have to go to the depth. But for the static, you cannot do depth profiling. Okay? You can see, you get a spectrum. This is a SIMS spectrum of the top monolayer. As I have shown you, just a top monolayer, and these are the elements present on the top monolayer. The intensities are the secondary ion emission cross-section of the elements present on the top surface. Do not be sure that the intensity high means high intensity of the element present. No. That is the beauty of the SIMS equipment. If you feel that the intensity of magnesium is very high in the spectrum, the peak is very high, it means magnesium concentration is high. No. Because magnesium cross-section is high. The magnesium emission cross-section is high, so you get the magnesium peak high. You understand my point? Never make that mistake while you make the SIMS analysis. Then you will lose everything. So you get the spectrum. So you have to correct it. Because I will show you what is the relationship between the concentration and the emission cross-section. That you have to know. And that expression is very complicated expression where the emission cross-section is involved. And the ion emission, just a minute, ion emission cross-section is so complicated phenomenon that even now we do not know what is the real mechanism in the SIMS. How the secondary ion emission is happening. It is very difficult to know. And in dynamic SIMS, you are going down and down and down. You are doing the experiment. You are measuring the signal intensity as a function of time. And you are going deeper and deeper. So you can really see an element present at any depth of the material. Because you are calibrating time as a function of depth. So you know precisely at what depth your copper was implanted, at what depth arsenic was implanted. You can really pinpoint that in the dynamic SIMS. And you can get a spectrum at any depth, and you can see this is a phosphorus. For example, this is a phosphorus concentration. This is a phosphorus concentration, and the peak indicates once again, if it is a concentration, this is secondary ion intensity, not the concentration. Once again, I'm telling you repeatedly, the intensity doesn't signify the concentration because the intensity has to be converted into the concentration. Unless you convert it, And unless you correct it, then you are not able to quantify. Because in the device people, like the Panasonic Corporation or any other semiconductor people, they have to quantify. But they do SIMS. Obviously they do SIMS. Because no other experiments, no other methods are so powerful. So SIMS has to be used. Because the lowest concentration present, that can be detected by the SIMS. Okay? It is destructive method. SIMS is a destructive method because you are digging the material. You are damaging the material, but it is most powerful. Yes, please.
We face one critical problem. The interfaces are not so straight. They were a bit broader.
Yes.
And how to actually resolve?
Yeah, because interface is broadened because of the interdiffusion.
Yeah. Because when the incident ion comes with an energy, is it any possibility that it can make the super atom to diffuse into the sublanes so that the interface gets broader?
It is possible because the incident ion has an energy. Incident ion has an energy. That's called the ion-induced damage.
Yeah.
That's another point. Because you are using a primary ion or incident ion having some amount of 3 or 5 or 6 keV energy. So the primary ion or the incident ion is itself creating damage. Okay.
But because we are coming from an industry
Yes.
where our interfaces plays a major role
Yeah.
because it is straightaway translate to the performance in market. So if you want to characterize the interfaces with this kind of instruments, we are facing this kind of a problem. Actually, my question is how to resolve it or how to overcome it.
That can be resolved, of course. As you can see, this is a static SIMS. There is no damage. The surface layer is intact. Your top surface layer is kept intact during the whole experiment. But in the dynamic SIMS, you have damaged the material. Some of the part of the material has been eroded. Okay. But the detection sensitivity is much higher in the dynamic SIMS. Can you tell me why? Detection sensitivity means what?
Get more amount of ions coming.
Because you are consuming more elements. You are consuming more element. You are consuming more material. You are consuming more material. So actually that means you are able to, for example, you have a very small concentration somewhere in the material. Okay? Can you do it by the static SIMS? No. Because unless you are consuming a lot of materials, you are not approaching that part of concentration. You follow my point? For example, you have a parts per million concentration of an element present somewhere here. You have to quantify that. What will you do? Static SIMS or dynamic SIMS? Dynamic SIMS. Because you have to come over here by gradually digging layer by layer you are digging and you are coming somewhere here. And you are consuming lot of materials. So it's a consumptive process or other destructive process. So by that, as you are consuming more materials, you are able to quantify small amount of species. So your detection sensitivity is getting higher. This is a very wonderful picture you can see. The more you have the incident ion current density or ion current, and more you have the atomic layers are removed per second, and more you have the detection sensitivity. Okay? That means parts per million atomic concentration. This is the incident ion current density. So more you have the ion current density, more you are removing atomic layers, more you are having the detection sensitivity. So you have to make a compromise while you do the SIMS. how much we need to fix where we have to get the detection sensitivity this much. Another point is important for people who do the SIMS measurements. You have a beam. This is the beam cross section. And you have to raster the beam, you know it. The beam has to be rastered over a large cross section. Your primary beam, in the SIMS machine I'm talking about now, your primary beam is not directing at a point way. It is rastering over X and Y directions. X, Y, and X this way. And while you raster, you are making a squared pattern and you are detecting the secondary ions from a central part. This is important while you do the measurement. This you have to fix it. Otherwise, you will has a Gaussian distribution of the ion. Every beam, primary beam, has a Gaussian distribution of the ion current. Every beam, you know. So that's why you have a Gaussian profile. You see this. And if you do the measurement from the central part of the rastered area, you have much sharper this kind of, you see, this is the concentration. So this is, you can see, you are loss of the age effect. This age effect is not lost that much while you do this kind of central part of the, if you detect the central part, you are detecting the secondary ions from the central part of the crater. Then you are not losing by the age effect. This is another important point. Which one?
Let's say in that crater, the whole depth, whatever depth I am trying to.
Crater is an uniform crater, X and Y, in the X and the Y directions.
Right.
The beam is falling in the that.
Right.
Okay? But you are measuring the secondary ions from the central part of the crater.
True, but you can measure from the, not from the central part.
Only the central part.
If you can only measure from the central part.
Yes, otherwise you will lose by the age effect. You see, the age effect is because the beam has a Gaussian distribution.
Alright.
So that's why while you make the crater, the crater has this kind of shape. But if you do the from the central part, you are not losing the age effect. So your depth distribution, your actual distribution as a function of depth is much more correct. Okay. Another point, this is all important instrumental aspects. So another point, you see, this is not a very good picture. Your beam, how much angle we have to fix now? This is another question. Your primary beam could be angular, it could be incident at any angle. It could be 10 degree. The primary beam can fall on the surface at 10 degree or 20 degree or 30 degree, 40 degree, etc. As you can see, at different angles of the impact, you will lose greatly of the secondary ion emission. Remember those points while you measure this through the SIMS measure. Because you have to, you see, if your energy is around 250 EV, you are constant. You see, for any angle of impact, your secondary intensity remains more or less constant. This is we have done it. Very important observation. So if you keep your primary ion energy very low, around 200 to 250 EV, whatever the angle of impact is, doesn't really matter. So these are all the physics experiments, not the real SIMS experiment for measuring concentration, but one before going into the actual measurement of the concentration, one has to do a lot of physics experiments, isn't it? That is important. One has to know how the mechanism take a role, or how the ion impact angle, but you have to fix it. At what angle of incidence we have to fix it. So remember these 2 points. Ion energy is important, and the angle of impact is important also in some cases. And you can see for the other energies how they are they are changing. Now I am talking about a little bit of instrumentation. Magnetic sector mass and mass spectrometer, where you have the very high mass resolution and you can get the exact mass. If you have a quadrupole mass spectrometer for the mass analysis, you can have very low mass resolution, not so much high resolution, but it can be very fast and it is also very cheap because it's very costly. And if it is a time of flight mass spectrometer or time of flight analyzer, then no upper limit in the mass resolution. This is very important. You can distinguish between 10,000 atomic mass unit and 10,001 atomic mass unit. Okay? Remember this point. Mass resolution means what? You are able to distinguish between two different masses of short difference. For example, 100 atomic mass unit and 101 atomic mass unit. Are you able to distinguish? What are the peaks look like? These two peaks have to be separated. The peak corresponding to 100 atomic mass unit and the peak corresponding to 101 atomic mass unit, they have to be resolved. This is called mass resolution. Okay? But in the time of flight SIMS, you can differentiate between 10,000 atomic mass unit and 10,001 atomic mass unit. You imagine the mass resolution. Even it has even a higher mass resolution and high throughput, very fast and very, with each pulse of primary ion, every pulse you get the whole spectrum, high throughput. This is the magnetic sector, magnetic sector. So you see, I will show you another figure. From the ion gun, ions are coming, light ions will be more deflected. You know why? Lorentz force is equated with the centrifugal force. mv square by r is the centrifugal force is equal to the BeV. B is the magnetic field, E is the electronic charge, and V is the velocity. Small v is the velocity. So BeV equal to mv square by r. If you equate this expression, then you get this. mv square by r equal to bz. Z is the charge, electronic charge. And so you ultimately get this. So the radius of curvature of the ion is proportional to the square root of mass. So the low mass will be having more radius of curvature. So you can see here that lower mass will be more bent, higher mass will be little bit less bent, and another one. So you will gradually, you are really making the mass separation. This is not mass separated. All masses are coming together. But while you put the magnet, sector magnetic field, you are mass separated. This is called the sector magnetic field mass analyzer. You see? Lighter ions will be deflected more and little more heavier, deflected at this. So you can gradually, you can change the position and you can really collect a particular species. This is another type of mass spectrometer. This is a quadrupole mass spectrometer. This is a quadrupole type of mass spectrometer where it's another kind of mass spectrometer, which you have the 4 quadrupoles where the ions are passing through and making oscillations, and they are transported into the detector. You are able to detect finally each and every single ion. Okay? You are measuring as a function of mass, you get. So you see the red one is transported and the black one is not transported. They are not stable. So this is another kind of mass spectrometer where you can see a particular ion has been transported So they are called the resonant, and which is not resonant, that is, they are not resonant. They are not being transported to the detector site. This is a quadruple mass spectrometer. This is the actually, I'm not going into the detailed part. This is another, it will take long time. So this is called the radio frequency, because these 4 rods, there are 4 rods here. These 2 rods are parallel, all are parallel, and these opposite rods are connected, and these opposite rods are connected. So these are the positive and this is negative. It's all a radio frequency voltage. And this is a DC voltage superimposed on the radio frequency voltage. So RF and DC combination is acting here. In that case, actually the ions are executing oscillations and will being transported to the detector. Only the resonant kind of masses, resonant ions will be obtained or will be detected by the detector. You see, this is the single mass scan line where this is a stable region, this is a stable, for each and every individual ion we can create a stable part and we can create another stable part. So this is a mass scan line. So all the ions here are being transported to the mass spectrometer. So, but this is stable, but this is not stable. This is not stable because every ion have to fall in the stability diagram. This is something different type of mass spectrometer. This is what I built myself. This is the radio frequency quadruple mass spectrometer. Very complicated type of mass spectrometer. And you can see, this is the machine what our laboratory has installed, and this is a radio frequency quadruple mass spectrometer. Okay, and this is a complete machine where we can do the ion imaging, secondary neutral mass spectrometry, and we can do the secondary ion mass spectrometry and everything. This is the instrumentation. And the time of flight is, what is the time of flight mass spectrometer? Time of flight means you have the ion gun, you have the vacuum part where you are creating the positive ions, and the positive ions are entering into an accelerator region. Just follow it. When you have the accelerating column, the lighter ions will be more accelerated, okay, and heavier ions will be less accelerated. So the lighter ions will, and after the acceleration part is completed, so after all the ions, when they are accelerated by the accelerating column, they are allowed to enter into a field-free region. There is no electrical or magnetic fields anywhere in the field-free region. Okay? And then you see, the lighter ions are more accelerated, they will move faster, and they will go to the detector fast. And then the little heavier ions will come after that, and then the even heavier will move even after that. So gradually you get a mass spectrum. Is the idea clear? This is the basic equation in a time of flight mass spectrometer. This is the basic equation. You see, energy in the accelerating column, the energy is the EV, V is the acceleration voltage. So V is the accelerating voltage, EV is the kinetic energy. It is equal to the half mv square. Okay? So you can see from the expression, so velocity is proportional to 1 by root m. In the time of flight mass spectrometer, you remember that the velocity of the ion is proportional to 1 by root m. So lighter mass will have higher velocity. So it means what? In the time of flight mass spectrum, secondary ion, time of flight SIMS, the lighter ions will be detected first, and then the heavier ions. So you are measuring as a function of time. Like this. This is the sample ions, okay? and this is the accelerating column, where you have an extraction of 30 kilovolt, for example, and all the ions are, when they are entering into the accelerating column, they are accelerated. But the lighter ions will be more accelerated, as I told you, and see, the lighter ions will be transported faster, because this is field-free region. No field here, and this is the detector. Now, this is a very important question is there. A single ion, for example, M1, M2, M3. M1 is lighter, M2 is heavier, M3 is even more heavier. Okay. Now, M1, this is not a single ion. This M1 element, M1 ion can be many ions of M1 species. Okay, so you are detecting only M1. All are going. But these ions have the kinetic energy distributions. Okay, so it is important to distinguish the energy also, because these M1, all, for example, you have four ions of same mass M1, then they can have a difference in the energy. So you will lose the resolution, That's why there is the next slide will show you how that is solved. Okay, this is important before that. In the time of flight SIMS, you have a beam generation, first part, where you are using ions are produced using sources like liquid metal ion gun, like gallium, bismuth, gold, etc. These are all coming from the liquid metal ions. Or gas clusters, for example, C60, or maybe argon cluster. These are the ions usually used in the time of flight SIMS. Okay? And then this beam is not pulsed. This is not pulsed, but you have to make it pulsed. How to make it pulse? Because pulsed primary ion in ToF is generated by taking a continuous beam and then chopping into extremely short bursts by combined with using pulsing detector. You have a pulsing deflection plates which is moving very fast. Then you are getting a pulsed beam within 0.5 to 2 nanosecond duration. So by blinking, by pulsing electric, and by combined with buncher cavities, or using, for example, this kind of deflection plates like the bunching or by blanking. By the chopping and blanking, you can do the pulsed beams, the pulsed ions, and every pulse, every individual pulse, you get the whole spectrum. Okay, because you are measuring into the detector. The detector is measuring whole spectrum. Detector is measuring M1, M2, M3, M4, all the ions are measuring. You get a whole spectrum of positive or negative ions. This is important. And then what is the detector in the time of flight SIMS? Time of flight SIMS, this is the detector. It's a channel plate detector where you have a series of electron multipliers, and this is the electron multiplier. You can see there are the dinodes. So the electron is multiplying, and we have a bunch of electrons. Many 10 to the power 6 or 7 times electrons are produced. But here you get an avalanche of electrons, because this is series of multipliers are in parallel. This is called channeltron detector. I hope here in the machine also you have the similar kind of detector, channeltron detector, which is nothing but a parallel combination of many electron multipliers, which are detecting lots of electrons, because your positive ions are detected by creating electrons. So electrons are detected. So this is some kind of detector, which is, there are diodes. This is called diode. This is diode. And every diode has increasing potential. So you have more and more electron multiplication. Electrons are multiplied here. Again more multiplication. You are gradually getting lot of electrons output. These electrons these electron current you are measuring by the detector. You follow my point? So this is the channeltron detector. This is called the diode type of detector. When you have a continuous then you have, in the channeltron detector, you can have this kind of continuous diodes, where the materials is of lead silicide glass, and here you have copper beryllium diodes. Okay, this is too much technical.
And the electrons are coming from?
What?
The electrons are, so ions, right? From the ions, how do I get the electrons?
When ions, the first ion, for example, coming from the mass analyzer, ion is falling into the diode. And diode is, electron is emitted. Because ion is falling onto the diode of the detector, first diode, but this is ion, but this is electrons. But you are measuring actually the electron current, not the ion. The secondary ions are ions, but you are measuring in the detector the electron, the avalanche of electrons. Okay? So this is electrons out. You are measuring the current. And you are telling, okay, this is our detector. This is our, the intensity of the secondary ions. Actually, this is convert that much of ion is creating that much of electrons. Okay? So you know precisely that your signal, if it is more signal, means here even more signal of electrons, more current. You can do the mass spectrum in the ToF-SIMS. You can do 2D imaging. You can do the 3D imaging. You can do the mass spectrum in the depth profiling mode, and you can do the 3D imaging. All are possible. And another important aspect, what I was telling you, this is very important. You are not making any energy calculation here. In the ToF-SIMS, one important point that you cannot compromise with the resolution. So that's why you have a reflector. So where you have these kind of splits, these are series of retarding potentials, more retarding, more retarding, more retarding. And the higher positive ion of a certain mass, they can have different energies. Okay? So the higher energy will go deeper, and the lower energy of the same mass. I am talking of the same mass now, because you have mass analyzed. Okay? In the time of flight SIMS, you have already made the mass analysis. You have detected, you have in the detector, before coming to the final detector, you have a particular ion. This ion, all are the same ion, remember, of say for example 100 atomic mass. But this is having 5 eV energy, 6 eV, 7 eV. Energy can be different. So unless you do the energy separation, you will lose in the resolution of in the detector intensity. So you have to match. How? We are using a reflector. So the higher energy will go deeper, will be reflected back, and the lower energy will be reflected from here. Finally, they will match at the same point, so that the resolution is not compromised. This is very important in the ToF-SIMS. You can see. As I told you, secondary ions have a wide distribution of kinetic energies. This is very important. Please remember that. In the ToF-SIMS, this is very, very important, because you should not compromise the energy resolution. So ions with higher kinetic energies penetrate deeper. Okay? Penetrate deeper. Lower energy ions will be reflected earlier, and this is reflected earlier. But they are finally catching together. Okay? So this focusing, there is a focusing system. This focusing mechanism allows faster ions to catch up with the slower ions, minimizing the flight time spread at the detector. So you are not losing the resolution. Yeah. This is there is a reflector plate actually. They have to reflect. They will be reflected. Because this is higher potential, this is lower potential. So they will again come back gradually. Yes.
When we analyze a sample, there are multiple combinations made. And there are some cases where two combinations may have the same sort of an basic ratio as well. So in that case, if the molecule is unknown, you want
Okay.
to resolve it.
Very good question. Yeah.
To actually
Yeah. You are telling that these two species can have the same mass.
same mass.
Okay. That's why I need a chalkboard. For example, you have two masses, M1 and M2. Okay? M1 and M2. M1 and M2. Same masses. Okay? But how to get separate? For example, CO. What is the mass? 12 plus 16. How much? 28. What is N2? How to separate? How to distinguish? Very important question. No, isn't it? But this is the mass number, atomic mass, but not the actual mass. Actual mass is, this is 28.0001. This is 27.995, for example. You follow my point? This is not the real mass. The real mass is 27.001, 28.001 and 27.995. So you have a mass difference. So delta M is the mass difference. 28.001 minus 27.995. There is a mass difference. So maybe it is something like 0.0001, for example. So your resolution, R is the resolution is the M by delta M. M is the average of these two divided by delta M. So you can get unless your machine has a mass resolution of that much, you cannot distinguish. The question is this. But you can distinguish by a separate mechanism. This is also another very important question. You will often face it in the laboratory. How to separate? Oh, okay. Now, for example, your machine is not able to give you that much of resolution. For example, resolution M by delta, imagine M is the average. For example, the average is 28. For example, average is 28. And what is the delta M? 0.0001. It's a huge. Does your mass spectrometer cater that much of resolution? I guess no. It's impossible. So you have to have a separate mechanism. This is the same question I had the same question when I started the work in the SIMS. How to separate? Then I imagine their kinetic energies must not be equal. Kinetic energies must not be equal. So if you can now separate the kinetic energies of those two species, then possibly you can able to distinguish. One, if you make a plot of energy, and this is the intensity. Your N2 will be like this. This is N2, and the CO will be like this. So if you do the kinetic energy analysis of the species, you will certainly have the differences in the energy distributions. So from that you can distinguish, unless you cannot distinguish. You follow my point? Is it clear to you? So these are all you have to play around. When you do the SIMS, you have to play around that, okay, how to get the separated? How to do the kinetic energy distributions? etc. etc. So many points, so many questions you may come, you may face. I don't think I have so much of time, no? But I will take maybe 10 minutes more. Because I could have given series of talks because I have 500 slides here or maybe more.
You plan to have more?
No, in future. No, I'm just kidding. If I have to give a series of talks, then I can stop here. Then tomorrow I will start fresh again. So, because so many slides are, it's impossible for me. Okay, the 500, I think I have about 100 slides. Yesterday night in the guest house, I just picked up so that I will give you some essence of the subject. So many important things I have to tell you, but I don't have time. I have to go to the hospital.
Next time, we'll have it next time.
Unless my wife is back home with full health, good health, I cannot make any plan. Okay, I should not go because these are all very, very mathematical of the SIMS. Many questions, the junior guys will have questions, yes, will have many questions. What is this mechanism of secondary ion emission? Very important. How the ion formation is taking place. Because I told you the particles are emitted. No, I told you that due to the primary ion bombardment, secondary particles are emitted due to sputtering. I told you. But I told you that point not 1% are the ions. How those ions are being formed. Very important question and very important thing. Nobody even now knows exactly, precisely the mechanism of the secondary ion formation. Okay, so this is an expression what I have used. This is the Meghnad Saha, you know. You know this gentleman who was a big astrophysicist, and under his name, my institute, Saha Institute of Nuclear Physics, he is M.N. Saha, and he gave an equation. This equation was basically he used this equation to measure the temperature of the solar corona, sun or star, etc. So Meghnad Saha actually gave the expression for that. So he actually gave the main expression was this. This was the main expression of M.N. Saha. A similar expression was a little bit altered, and we have used, by altering that expression of M.N. Saha, we have used this expression. And this is actually the secondary ion emission cross-section. You see, this is the positive ion emission current, positive ion emission intensity. How many positive ions are here? In X is the species. X is any species of interest. Say, for example, you are measuring carbon. So this is the carbon plus. How many carbon ions divided by how many neutral carbon? This is called the secondary ion emission cross-section. Do you follow my point? This is called the emission cross-section or the degree of ionization. This can be measured using this expression. Okay? But this expression where you can see that T is the temperature, where because the ion, when ion is falling, the primary ion is being incident on the material surface, there is a local plasma due to the ion impact. And that local plasma having electron, ions, positive ions, negative ions, and everything there, all are in the thermodynamically equilibrium state. And in that case, this is the expression, where T is the temperature of the plasma. And this is the ionization efficiency. So this K is the Boltzmann constant. This is a very long expression, and these are the partition functions of this is the partition functions of the electron partition function, of the positive ion partition function and the neutral partition function. This is a very complex equation where each and every parameter one has to find out, then you can really measure Nx by N0. Secondary ion emission. Your intensity, what you see in the spectrum, okay, that is a reflection of this, not the concentration. I told you many times to you. The secondary ion signal, what you see in the same spectrum, each signal doesn't reflect, is not really proportional to the concentration, but proportional to the ionization efficiency.
And so the efficiency, won't that also depend on the concentration?
Not necessarily. That is the difficult drawback of the SIMS. You are thinking, oh, I have a big signal of carbon. It means there is a lot of carbon there. No. You have to make a correction. Unless you do the, it will take long time to tell you how to do the corrections and how to, because unless I go to the laboratory and sit together with you, how to do the data analysis, it is impossible for you to tell right now. Only thing for your understanding that secondary ion intensity is reflected by the secondary ion, the ion emission cross section. Is it clear to you? Okay. So to answer your question, say you want to know the concentration of calcium and magnesium. You are doing SIMS. You have a calcium peak, you have a magnesium peak. And of course, the peak is coming at the right mass because it is a mass spectrum. Okay? So, calcium peak this much, magnesium peak this much. Does it mean that calcium is higher intensity in your material? May not be. Because calcium emission cross section is higher. So you get higher intensity of calcium in the spectrum, and you have lower emission cross section of magnesium, you get magnesium intensity less. Okay. Okay, I should skip many slides, sorry. Now I should tell you one thing. How to make the correction, as you told. Just one expression. This is I developed expression. This is a very good expression to understand. This is the secondary ion emission cross section. Secondary ion current, what you measure. To answer your question, this is very important to know this expression. This is actually the ion intensity what you measure for calcium. And this is the actual concentration of calcium, Cx. See, there are so many parameters here. You have to know each and every one. And this is the ion emission cross section. So the ion emission cross section beta for a particular species is important to know the concentration of the species. You understand my point? This is,
If the concentration is higher, that means intensity would be higher.
yeah, but this may not be proportional. You agree my point? You see, the concentration is higher, you should get the higher intensity. You are right. Unless this is also linearly proportional. But this beta x may not be linear with the Cx. Unless you know precisely the ion emission cross section for the species X, you are really not able to get the measurement of the concentration. So this is an expression. But from the simple expression, so actually this is the current, primary current, what you are using as an incident ion. This is the sputtering yield. This is the secondary ion emission cross section. And this is the Fx is the whole from this to this. From this to this is the constant. It's the constant depending on the geometry of the equipment. this is you see, here I have written down the fractions of the ionized particles, what are entering into the energy separated, energy window. Because secondary ions have a large energy window. So we have to select out a certain energy window, delta E. So this is the solid angle, delta omega. How much ions are, this is the fractions of the ions entering into the solid angle of, because your detector has a solid angle. Okay. And this is the transmission factor of the equipment, your mass spectrometer. And this is your detector efficiency. Unless you know all this, including this one, you can get a very simple, you can measure this IP, okay? You can measure sputtering yield, very simple. You can measure, even the constant is, you can calibrate from your table. But how to measure this beta X? This is, I am repeatedly telling you, because this is the most important and most tricky thing, that the ion emission cross-section is difficult to measure. That's why secondary ion measured value, how to calibrate or how to convert into the concentration, that is the most important part in the SIMS experiments or SIMS data analysis.
I have one question. There are many molecular dynamic simulations available for any sputtering phenomena.
For the sputtering phenomena, yes.
And we can always calculate the concentration of ions versus neutrals in those molecular simulations.
Yes.
Can that information be used for calculating this beta?
No, because beta is another process. In the secondary ion, initially when you have the sputtering, you are having the neutral particles. But the neutral particles in the secondary ion, your chamber in your machine, in the environment, vacuum environment, some of the ions get, positive, some of the neutral particles get ionized. And that is signifying the emission cross-section. That is not exactly what you are telling. Okay? The positive ion, the transformation from the neutral particles to the ion, that is deciding the emission cross-section. That is not there are beautiful, methods how to bypass that problem. You can bypass the problem and you can quantify. And that's the very beauty of the experiment. Okay, I want to, because I'm telling you a very complicated part is the secondary ion emission cross-section measurement. Okay, can we bypass that thing and we can get the idea of the concentration? That's also possible. That is what I have developed, and I don't have that much time, but I will only show you that this is the method. Okay, there are many techniques I should tell you. Okay. How to, as I told you, because the ionization emission cross-section is a tricky parameter and is dependent on your surface, because your surface, your top surface may have many impurities. You are measuring the magnesium concentration. You want to measure the magnesium intensity. The magnesium intensity rapidly changes depending on the oxygen, depending on your surface concentration, surface chemistry. You follow my point? Your top surface chemistry is very important to give you the idea of how much magnesium intensity will look like. So it is called the matrix effect. That means the secondary ion emission cross-section is changing. Why I told you it is difficult to measure? That question comes, no? Because it is difficult, because it is changing always on the in instantaneous surface chemistry. Shall I go back again to the expression? Then you will understand. Yes, see, this one. I told you, the concentration of a particular species is proportional to the secondary ion intensity. You can measure the intensity by your detector, and you can get the concentration if you know all the parameters. True? But you can measure this one, you can get the idea of the whole constant part, and you can even get this transmission, everything you can get. But this, how can you get it? Not possible. Because why you are not able to get it? Because this can be, either it can be very high or it can be very low, depending on your top surface chemistry. Your top surface chemistry, surface environment can change at any moment. So that it's called the instantaneous surface chemistry plays a big role in this beta X. And that is giving the matrix effect. This is the matrix effect in SIMS. When you do the SIMS in the laboratory, you would see there are literatures, they are talking lots about the matrix effect compensation. Okay. Now, I will show you a couple of slides that matrix effect compensation you can bypass. You can really prepare materials of known concentrations. Okay? You want to measure the unknown magnesium concentration by the SIMS. Now, you are really preparing known magnesium concentrations by op situ. It's an op situ measurement. You are having known concentration of magnesium in a sample. Okay, you get it. You are making another sample of higher magnesium concentration. So if you prepare a series of samples with known magnesium concentrations, you can get a calibration curve. And from that you know the unknown one. This is one very simple. Yes. So that's called the calibration curve method. Where you are drawing a curve where you get all known concentrations. And from your SIMS measurement, okay, you can get this much intensity. That means, okay, it falls in this region. This is the concentration.
Whether they provide any standards for?
Yes. There are standards. But how many you can have standards? Maybe 10 standards have been given by the company. So you can have you can prepare standards by using ion implantation. Okay. Another method, just try to follow my point. Another method, I'm once again using the board. As I told you, the secondary ion has a long energy distribution. Or if you measure the ions of higher energy values, this part, not this part. This part is very sensitive because they are close to the surface. Low energy part. Understand my point? The secondary ions of low energy, they are close to the surface. They are in the surface, close proximity of the surface. So they are influenced by the surface chemistry. But if you are able to measure the secondary ions of higher energy, they are far from the surface. They are not looking at surface chemistry. So you can minimize the surface chemistry from that measurement. But what is the difficulty in that? The difficulty that the detector doesn't have the capability of measuring this much. Because these are very high energy part of secondary ions, maybe about 5 keV or maybe 6 keV or 7 keV. This part of detector cannot detect because the intensity is getting very low intensity. The detector is not able to detect that much of intensity. Another part is there to bypass. If you detect, I told you this much, this one just now. If you detect secondary neutrals, my question is very simple. I will not detect the secondary ions. I will detect the secondary neutrals. Because I told you, 99.9% are neutrals. Okay, if I detect the neutrals, then it will not be influenced by the surface chemistry. Because these are not ions. So no matrix effect. You can quantify very simple way. But can you do that? Because these are the secondary neutrals. How can you do the mass analysis of neutrals? Not possible, no? Very difficult. In that case, you have to ionize again. You have to make a post-ionization by electron bombardment. Then you are allowing to go into the detector. Then you are eventually measuring the secondary neutral mass spectrometry, and you are, getting the matrix effect minimization. Instrumentation becomes more complicated. And this is very the most important part, or one of the most important part I am now going to tell you. Slow, hyperthermal, highly charged ion. Your positive ions, what you are using for bombardment, they are not singly charged. They are multiply charged. For example, if it is, this is your surface, this is your primary ion, okay? And this is your secondary ions. Okay? This is not singly charged, but this is, say for example, Cu, say, this is just for example. If you take a highly charged copper, where all the electrons of the copper have been removed, say copper 64. How much is the atomic number of copper? 64? I'm not able to remember. 29. So, is 29 is the number of electrons in the copper? Okay, atomic number? Okay, 29 plus. That means all electrons of the copper have been removed. What is this? Multiply charged ions, highly charged ions. So it means all electrons have been stripped off from the copper atom. Now what will happen if it falls on the material surface? Then, since it is all electrons have been stripped off, this is highly charged, very, very highly charged. Here at the surface, these highly charged ions, when it falls on the material surface, they do not have any kinetic energy because they are hyperthermal energy. So mostly they have the potential energy. If you strip off electrons, if you strip off 29 electrons from the copper atom, they have lots of potential energy, no kinetic energy. Now, if you allow to make incident of this copper 29 plus on the material surface, here many electrons from the conduction band will try to fill up the vacancies of copper immediately. You follow my point? Because it is highly charged. When it comes here in the close proximity from the surface electrons, they will try to fill up the vacancies immediately, making lots of electrons, making lots of positive ions remaining on the top surface. There will be Coulomb repulsion. These positive ions, there will be a lot of positive ions will be assembled here very quickly, and there will be big Coulomb repulsion. And this Coulomb repulsion, these positive ions, you are now measuring by the secondary ion mass spectrometer. You follow my point? Then you have no matrix effect, no secondary ion emission cross-section problem, no matrix effect problem. Everything is possible. This is the most beautiful technique by the slow, highly charged ion bombardment and doing the SIMS. We have done one experiment using that. You can see the secondary ion emission cross-section is almost constant if you allow the highly charged ions. Okay, I think this is another experiment, this is another technique where using this kind of M is the element of interest, and this is the alkali element A. So if you use now the alkali element like the cesium, and if you monitor this kind of molecule in the SIMS, it is not really influenced by the surface chemistry anymore. This is the most important part in the SIMS. You can directly quantify the material. You don't have to see the catalog. You don't have to see any literature. You are measuring M, this kind of M, this A is the alkali element, like cesium, like rubidium, etc. If you take this kind of molecule, if you detect by your detector, and if you measure that intensity of ion is directly proportional to the concentration. Okay, I have done this. This is the method what I have developed, we have developed, my student and myself, and this is now globally accepted phenomenon in the SIMS community. Now even the National Panasonic Corporation of Japan is using this technique to quantify the materials. And in fact, they invited me once in Japan. I gave this talk, and they were very pleased to listen to this talk, how to quantify the SIMS, because this is a burning problem of SIMS to quantify the materials because of the matrix effect. I will simply give you some examples. Now, just a minute. What is this kind of molecule? I told you the alkali element, and this is the alkali element, cesium. You are bombarding with the cesium now, and your element is your copper. And the copper, sputtered copper atom, and the secondary cesium or the sputtered cesium are very low energy. Both are of low energy, but they are coming in the close proximity, and they are making a molecule. They are making a pseudo molecule. Do you follow my point? You are now using not oxygen, not or rather other elements. You are using cesium as bombardment, for bombardment, and you are measuring copper or measuring zinc or magnesium, whatever it is. So you have sputtered cesium plus, which is very low, of low energy. This is also sputtered of low energy. This is cesium plus. The cesium plus this is the primary cesium plus. When they are coming in the close proximity, see, they are forming a pseudo molecule. They are forming a pseudo molecule. They are coming in the close proximity. And this electric field of the cesium influences this M neutral molecule, and it gets polarized because they have the electron cloud and the nucleus. So what is happening? It is polarized. Now when they are polarized, it means electron cloud is shifted from the positive nucleus. So when they are polarized, this electric field of the cesium ion then there is a binding, or there is a force between this interaction potential between this cesium and this dipole moment. Now if a force is acting on the dipole moment, what is happening? There is a dipole, there is a force is happening. You see, this is happening. So the dipole moment, this is the dipole moment, and so finally what happens, the dipole moment, so the force, this dipole moment is interacting with the electric charge of the cesium. That makes the pseudo molecule. That pseudo molecule you are measuring now. You are measuring the pseudo molecule intensity, and that intensity will be directly proportional to the concentration of the element. No matrix effect. Okay? And this is the last slide. You see, M0 is a neutral M. They are combining with the cesium plus, and this MCS molecule is forming. Now, even cesium can be 2 cesium, can be 3 cesium. So this can be even higher molecules as possible. But this molecule is very important. So there is a strong correlation between the MCS intensity of and atomic polarization of M0. Okay, I am now stopping here. And this is, we have done lots of measurements from lots of elements. We have seen the intensity of MCS kind of molecule to the, this is silicon, this is silicon cesium plus, and as a function of the atomic polarizability. And we have seen there all elements are falling on the same, this line. It is very important for the SIMS measurements. Okay, I think there are many mathematics here now, and so, but this is, lastly I will show you that composition analysis. This is the last recent measurement what we have done using the MCS molecule. This is a neutron mirror. This is a silicon iron neutron mirror. So neutron has no reflectivity, you know. Neutron can't reflect. Neutron can penetrate very deeper. A neutron cannot be reflected. How to reflect, how to get the neutron reflected? So if you prepare a neutron mirror, then you can reflect the neutrons. Okay, how to prepare, that is another technical point, I'm not telling, but only thing you are preparing a thin multi-layered structures like this, like silicon film, iron film, silicon film, iron film, silicon, iron, that way a huge structure, like, for example, 80 period structure, 160 layers of silicon and iron. And then you get a mirror. And then you see, this is the SIMS, this is the SIMS of the entire stack. This is the SIMS, and this is the MCS SIMS. And this is the intensities of silicon and intensities of iron. They are directly reflecting the concentrations of silicon and iron. This is another thing. This is copper gold. Copper gold multi-layered structure. We have done the imaging and interface. This is the interface. They are very highly miscible, copper gold. So copper has a high tendency of mixing with the gold, and copper gold can be intermixed and make an alloy. And we have obtained a peculiar kind of alloy, what is not normally obtained in the nature. It's called the novel alloy. So we could fabricate a novel alloy, and that we could determine by the SIMS. Just one slide. This is the SIMS of, you see, that's the multi-layered structure. Copper gold, this is the cross-sectional TEM. And this is the SIMS. This is the intensity. This is the black one is the copper. Red one is the copper gold. And the green one is the copper 2 gold. And the blue one is the copper gold 2 copper. So these are different kind of alloy. And these alloys are forming across the interface. This is the interface. This is another interface. This is another interface. So across the interfaces, because they are intermixing, no? So without SIMS, it is impossible to know. Do you follow my point? Without SIMS, it is impossible to get an idea how the intermixing is happening across the alloy interfaces and how to get the different kind of alloys. And if your instrument is having high resolution, depth resolution, you can differentiate these kind of different alloys across each interface. I think I should stop here. I gave you just an idea of the SIMS and the ToF-SIMS, the instrumentation, and some basic things of SIMS. Of course, there are many things of SIMS. It is not possible to cover in one page. Thank you very much.
Actually, we have learned much more than we thought that we would, and there is so much more to learn, which justifies that future workshops that we are having. Unfortunately, we have to stop here now because we have another speaker waiting in Japan. So already we are slightly delayed. So once again, let us thank Professor Purushottam Chakraborty for coming all the way in spite of all the problems that he is facing, and wish his wife a speedy recovery as soon as possible so that he can come again and he has a, better, and he can come again and inspire us and educate us about it. We hope that he'll be doing that.
I would like to request Professor Mitro to hand over a token memento. Sir, much kind. 1 minute. Take a photograph. Thank you. Thank you, sir.